Hello everyone, good time. I hope you are all fine and doing well. So far, we talked about the methods that we have based on the energy and based on the work done by forces for finding the deflections in structures. We talked about it in the presentation files, and today we are going to solve a few more examples to make sure we completely understand the procedure and we know how to use the methods in finding deflections in different structures. So over here you can see the first example. This truss, as you can see, is the same truss that I solved in the presentation file. The only difference is that in the presentation file I solved this problem by using Castigliano's second theorem, but over here I'm using the virtual work method for solving the problem. By looking at both of the problems, you can see how different are the two methods, and you can also compare the amount of effort that we need for solving problems and how much maybe time you can save by picking the quicker method. In the exam, I will specifically mention the method that I want you to use for solving problems, but in general, comparing these two examples, and I think I have one beam example, comparing these examples and the different methods that we have for solving them can give you some idea about the methods and how we can use them for solving problems. So this one is this truss. We have a hinge support at one side and a roller support on the other side. We have 5 members in this truss, and as you can see, we have one horizontal load at point D and one vertical load at point B. The question is asking about the horizontal and vertical components of the deflection at joint B, this joint over here, and it is also asking us to use the virtual work method for solving the problem. So we know whenever we want to use the virtual work method, there are two analyses that we have to have for solving the problem. The first one is analyzing the structure under the given loading. Like for example in this one, for this truss, I have to analyze the truss under those loads that are applied at joint D and B. That's the first step. The second step is to remove this loading and apply the unit loads, which are the virtual loads, at that specific locations where we want to know the deflections. In this example, we want to know the horizontal and vertical components of the deflection at joint B. So I have to have I have to have two analyses for the virtual load. One is when we consider a virtual load, a virtual vertical unit load at point B, and the other one a virtual unit load for the horizontal load or deflection at point B. As you may remember, I said the good thing about these energy methods is that it is easier to use them in comparison to the geometrical methods for finding the deflections. But the problem is that, or the negative points about these methods is that for each deflection that you want, you have to have one sort of calculations or one separate attempt of calculations for each deflection. That's why when I want to apply the unit load for using the virtual work method in this problem, I have to have two different analyses just for considering the virtual load. One is the virtual unit load in the horizontal direction at point B, and the other one is the virtual unit load in the vertical direction at point B, because the question is asking about two different deformation or deflection values in the question. So the first step is to analyze the structure under the given load. That's what is happening over here. I didn't go through the steps of analyzing the truss itself, because that's what we did in the previous chapters. And of course, in the second exam, you reviewed the procedure, and by now you are completely familiar with the steps of finding and analyzing the forces in trusses. So we analyzed the truss under the given loading or under these two joint loads, and these are the results. Now I have to remove the actual loading and apply the unit virtual loads. One of them is this situation, a unit horizontal load at point B, because the question was asking about a horizontal deflection at point B. And the other one is this unit load in the vertical direction at joint B. And this is because the question was also asking about the vertical deflection at joint B. Considering these two, I have to analyze the truss under these loadings, and as you can see, the results are shown. When I have a unit load at joint B, these are the analysis results, and when I have a vertical load at joint B, these are the analysis results. Once we do that, we have to just return to the equations that we could develop in the presentation file for the virtual work method, specifically for truss structures, and use them for finding the deflections. These are the equations that we had for truss structures. One, which is that unit load multiplied by the deflection is equal to the summation of virtual force in each of the truss members multiplied by the force because of the actual loading multiplied by length over E and A. And this is for the case of having the horizontal deflection or finding the horizontal deflection at point B. For the other situation in which I want to find the vertical deflection at joint B, the formula is the same. The only thing that changes is the parameter. Over there I was looking for the horizontal deflection. Over here I'm looking for the vertical deflection, and this term FVV is the virtual force in the truss members because of that virtual load that I considered or applied at joint B, that virtual unit vertical load. The only difference in these two equations are this FVH and FVV. This FVH is the virtual force in the truss members because of that horizontal unit load, and this FVV is the virtual force in the truss members because of that vertical unit load that we applied at joint B. As you know, I'm always using these tables to put everything in them, and it can kind of makes the solution easier, and we can have all the values next to each other. This will help you a lot in terms of finding the summation of the values, and basically you can do the calculations quicker, and you can also track the forces that you have in the members. So we have 5 members in the truss. This is the truss that we are talking about. F in the equation are these forces, FVH are these forces, and FVV are these forces. These are listed in the table, length of each member, and then as you can see in the equation I have to multiply the force FVH by F by L. That is done in these two columns, and then I have to consider the summation of these values divided by EA. Over here you can see the summations, just forces multiplied by each other and also by length. And now in these equations I'm calculating and including the EA in the equation. EA is just based on the properties of material that we are using in the truss. Those are given in the problem. As you can see over here, E and A are given. The only thing that you have to make sure when you are finding the deflection, or the other thing that you have to make sure when you are calculating the deflection, is the units that you have in your equation. Over here, when I was calculating the forces and multiplying them by the length, everything was in terms of kilonewton and meter. So that's what I have on top of the ratio. On the bottom, where I have the EA, the final values should be in the same units so that we can calculate the ratio and find the final value. E is 200 gigapascal and A is 1200 millimeter square. I know each gigapascal is 10 to the power 9 multiplied by Pascal, and Pascal is just force per area, or is the unit of pressure. So that is force per area or Newton per meter square. Now that I can see the Newton and meter, I have to change them to kilonewton and meter. So this meter is fine. This Newton should be changed to kilonewton, which is done later by just dividing the final value by 1000, and this millimeter square that we have as the area or the cross-section area of the members is changed to meter by this ratio over here. I know each meter is 1000 millimeter. So at the end, I have this unit and this value as the EA in my calculation. Just putting it in the equation and in the ratio that we had over there. As you can see over here, we can find the horizontal deflection at B as 0.35 millimeter, and it is positive, which means that the deflection is in the same direction as the unit load that we applied to the truss. I applied the unit load from left to right, as you can see in this direction. I got a positive value as the deflection, which means the deflection is in the same direction as the unit load that I applied when I was analyzing the truss and when I was considering the virtual loading on the truss. That was the first part. The other part that I yet need to calculate is the vertical deflection. For that, we did calculate everything in the table. I just need to put this into this equation. The summation of forces multiplied by each other and also the length is calculated over here. So that values is written here. EA we did calculate it earlier for the last calculation, so that is written here, and by just calculating the ratio you can see the vertical deflection is 3.32 millimeter. Again, it is positive, which means that the direction of the deflection is the same as the unit load that I applied as the virtual load. Over here it is downward. I got a positive value for the deflection, which means the directions are the same, and the vertical deflection is downward. So as you can see, we could solve this problem. We could find the deflections at point B, both horizontal and vertical, by using the virtual work method. You can look at the presentation files and you can see in one of the examples that I solved over there, I analyzed and solved this problem by using Castigliano's second theorem. You can compare the methods and see how things are changed in the two methods. So after this, let's move forward to the second example, which is this truss. And the question is asking about finding or determining the vertical deflection at joint C, this joint over here, because of a temperature change, which is a drop of 15 Fahrenheit degrees in temperature in members AB and BC, and a temperature increase in member AF, FG, and GH, and the amount of increase is 60 degrees Fahrenheit. So, as you can see in this specific problem, we have to use the virtual work method as the question is asking, and the type of loading that we have in this truss is not like previous situations where we had the forces applied to the joints. In this problem, the loading is because of the change in the temperature. You know, when we have a member, if we increase the temperature, the member will expand. And by expansion, it is going to push the members around it. So it will act like a source of force, and it will apply some force to the whole truss. That way, we have to analyze the truss and see what is the force in other members, and we can also find the deflections. That's what's happening over here. We have to use the virtual work method, and the question is asking us the vertical deflection at joint C because of this temperature change in the members that are listed in the problem. So let's see how we can use the method and solve this problem. So the steps are the same. You have to follow the same procedure that we had. The only thing is that the loading is different for this situation that we have for this truss. At first, I have to analyze the structure or analyze this truss under the given loading, which is the temperature change. I have listed the members that are experiencing the temperature change, and I also included the amount of change that we have in the temperature for each of these members that are listed in the problem. Now, for analyzing this, I have to know the forces in the members, right? Based on the basic knowledge that we have in physics from high school, I believe, we know that the change in the length when we change the temperature is equal to alpha L delta T, right? We also know that based on the mechanics of material for axial members, the change in the length when we have some force in the member is equal to FL over EA. Putting these two equal to each other, alpha L delta T is equal to FL over EA. Now, these two L's can be cancelled, and once I do that, we can see the force because of temperature change will be equal to alpha delta T, which is the change in the temperature multiplied by EA. So when we change the temperature of a truss member, the amount of force that will be induced in that member is equal to alpha delta T EA. Alpha is the constant that we have for the material whenever we change their temperature, and that is, as you can see, mentioned in the problem statement. So now I have analyzed the truss under the given loading, which means I could find the force in all the members because of the temperature change that we had in the truss. Based on this equation, I know what is the force in each of these members that are experiencing the temperature change. Now I have to analyze the truss under the unit load or under the virtual load. The question is asking about the vertical deflection at point C, so I have to apply a vertical unit load at point C. That's what I have over here. And then once I do that, I can analyze the truss and find the force in all the members. As you can see, I listed the forces that I could find based on the analysis only for the members that are experiencing the temperature change. Of course, the other members are also experiencing some force because of this unit load, but the thing is that based on the equation that we have for virtual work method, I have to multiply the virtual force multiplied by the force from the actual loading, which means that if there is no force because of the actual loading in the truss, then it is pointless to calculate the force in that member because of the virtual load, because that will be multiplied by 0, and at the end it will be just 0. You can calculate and find the forces in all the members, but I just wanted to kind of save some time in terms of the calculations. But it is absolutely fine if you find the forces in all of the members. So now I have to return to the equation that we had for the virtual work method. 1, or the virtual force multiplied by the deflection, is equal to summation of the forces because of virtual loading multiplied by the force because of the actual loading multiplied by the length over EA. In this specific situation, we found the force based on this equation as alpha delta T EA. Putting that instead of the force, this EA will be cancelled with the EA that we have on the top, and this will be the equation or the formula to use in the equations that we have for virtual work method. Alpha is just a constant value which is the same for all the members, so I am taking it out from the summation, and these terms are the terms that I have in the table. For each of the members I have the length, I have the amount of temperature change, and I also have FV, the force in the member because of virtual loading, and I have FV multiplied by delta T multiplied by L. As you can see, this is the equation that we have to solve for finding the deflection due to the virtual work method. So calculating this and adding all of them together, this is the summation. Now I can return it to the equation, multiplying it by alpha. You can see the deflection is minus 0.0176 feet. That is upward. Why is it upward? Because I get this deflection with a negative sign, which means the deflection is in the opposite direction to the virtual unit load that I applied. I applied the virtual load downward, and I got a negative deflection over here, which means the deflection of point C in the vertical direction is upward. I just changed this unit from feet to inch to just see the more sensible deflection value, and you can see this value is equal to 0.211 inches, and it is upward as I discussed because the deflection sign was negative and it is in opposite to the direction of the unit load. So as you can see, the procedure was very similar to the other examples that we had for virtual work method. The only difference was the type of loading, and in this example the loading was the force in the members because of the temperature change. Right? I just came up with the equation that we have for forces in the members because of the temperature change, and once I find that, I can use it in the equation of virtual work method and find the forces in the members. You can also have this example for the situation of having change in the length of the members. Let's say, for example, when they were fabricating these members, they made a mistake, or for some errors, they could find or they could fabricate these members with some length a bit longer or smaller than the actual length that they need based on the design or based on the geometry. It means that you have to press the member a little or stretch it a little to put it in the structure. That means the member will be in some force due to that initial pressure or stretch. That way you can have the same problem. The only thing is that the actual loading in the truss will be due to fabrication errors or initial construction errors in the members. But the procedure will be exactly the same, and you can follow the same procedure for solving the problem. That was the second example, and over here you can see we have the third example. And as you can see, it is showing us the situation of having members with initial length different than the actual length that we need in the truss. And because of that, we have to find the forces and deflections that we have in the truss. As you can see, it is saying determine the vertical deflection at joint D, this joint over here. If member CF is 0.6 inches too long and member EF is 0.4 inches too short, use the method of virtual work. So let's see how we can use this method for finding the deflections in this example over here. So let's follow the procedure that we have for the virtual work method and use it for solving this truss over here. As you can see, the forces that are created in the members are because of the initial length error. As I said earlier, this member over here is 0.4 inches too short, and this member CF over here is 0.6 inches too long. So over here you can see the location of these members and the initial length error. Those are mentioned in the members, and of course the deflection in the error in the members is equal to FL over EA. By having this equation and knowing it from the mechanics of materials, we know that the force in the members will cause such deflection, or in other way, the deflection will cause such force in the members. The question is asking about the vertical deflection at point D. So I have to remove the loading, in this specific case, these initial deflections, and apply a unit load in the direction that the question is asking. The question was asking about the deflection at point D. So I applied a unit load at joint D, as you can see over here, and then I have to analyze the truss. I mentioned only the forces that are created in the members that we have the error length, because as you know, based on the equation of virtual work method, we are going to multiply the forces in the members, and if, for example, one member is not carrying any virtual force, then calculating the force that it has under the actual loading will be pointless, because it should be multiplied by 0. That's why I only calculated the forces in these two members that we have the initial length error. So based on the virtual work method, this is the equation. In this specific case, I can replace FL over EA by delta, and this delta will be the initial length error or deflection in the members, right? This is just playing with the equation, and to be honest, this is the very basic form of the virtual work method. We said the work done by virtual forces applied externally is equal to the work done by internal forces and loads. That's 1 multiplied by deflection is equal to the summation of internal forces multiplied by their own deflection. These two works or energies are equal. That is the very basic form of virtual work method. So having this equation, I have to list the members that are experiencing the error length or the change in the length, and I have to also include the forces that we have in those members because of the virtual loading. Once we have this, we can simply multiply them by together and return it to the equation that we have, and by doing this, I can find the deflection at point D as -1 inches. It is negative, which means that the deflection is opposite to the direction that I considered for the unit virtual force. This unit load is downward, and the deflection that I got from the calculations is negative, which means the deflection at point D is upward, and that's what I have over here. The only thing that might seem a little different than the other examples is just the type of loading. Again, the forces that we have in the members is because of the change in the length. Because of the initial error, some members are too short or too long. This is how we should put them as the loading in the truss. And then once you do that, you can simply return them to this table. If it is too short, you have to consider it with a negative. If it is too long, you have considered it with a positive like this. And then the truss analysis under the virtual force is what we did several times before. I have to just put them in the table and then find the final value. I know these are new materials for you, so I'm gonna leave the rest of the time for you to repeat these examples solve them at home. And if you have any question, don't hesitate to send me your question. We can definitely discuss this through email or WebEx meeting. And I want to make sure that you understand these completely without any problem. You're going to see similar examples and problems in the final exam. And the final exam will be about calculating deflections based on these methods or the previous methods that we talked about in chapter 4. Thank you and take care.